After your quiz yesterday, we starting to talk about how signals are created or designed. What are the signals that are transmitted between transmitter and receiver? So we just looked yesterday at introducing, okay, everything's based on a sinusoid signal, a sine wave. And there's the general equation that we have on the previous slide.
So
yep.
The last question of the latest quiz yesterday.
Yep.
Can ask how long we have to wait for the web page.
Yes. Okay.
So we have transmit time as or total delay or just total delay.
So the last question on the quiz was how long you press, you link, then there's one packet that is sent to the server. So for that, you need to calculate the delay for that packet.
So it's just only the total delay or total delay as transmit time.
Transmit time is part of delay. So total delay, if you want to calculate, say the total delay is the time to get the packet there and for the response to get back. That's the total delay. That includes the time to transmit the packet, propagate, and all those other components. So, yeah, so the total delay includes the transmit time. So remember, delay is the sum of those four components: transmit time, transmit time, propagation time, queuing time, and processing time. Always, we'll keep it simple like that for those four components. So the question yesterday involved working out what those individual components were, and they're summing them up. With our signals, our general equation which is actually on the previous slide. A sine wave has some peak amplitude, some frequency, and some phase. Varying these three parameters changes the shape of our sine wave. Combining different sinusoids together, we've seen an example here where we add two together, gives us a different shape communication signal. And in theory, we can design any type of communication signal using a combination of sinusoids. Looking at our example here, ignoring the multiplier 4 divided by pi at the front, just briefly, signal A. What's the peak amplitude for signal A?
Signal A amplitude
1. Frequency? What's the frequency of signal A? 100. You'd get 0 marks if you answer that in the quiz. 100 hertz. We need to know the units. Hertz means repetitions per second or cycles per second. So 100 repetitions of the wave, the single sinusoid, per second. Phase, easy one. And the phase? Signal A has a phase of 0. There is no phase. There's no component here. Okay. Signal B has a peak amplitude of 1/3 and a frequency 300 hertz. Just using this general equation and working out what is F, what is the phase, and what is A. When we combine them together, just adding those, then This component has a frequency of 100 Hertz. This component has a frequency of 3 times 100. In that case, the resulting signal, when we add them together, let's write it down. Just adding these together. Just addition of them. The resulting signal, because the two components have frequencies which are integer multiples of one of them, then the resulting signal has a fundamental frequency of 100 Hertz. That is, the frequency of signal 1 equals 100 Hertz. So in fact, the frequency of this signal is the same as this one. That's illustrated on the next slide, where the top one is has the shape of this signal. The second one has the shape of this signal, where we see it's 1/3 in amplitude and 3 times the frequency here. And the bottom one is the summation of those two. Same frequency as the top one. That is, we see the period from here to here for a single waveform, a single repetition, is the same as the top one. But of course we have these variations because we're adding on this other signal. Here, just for simplicity, I've left off this multiplier of 4 divided by pi. All that does is shifts the peak amplitude of the signal. If we times by 4 over pi, everything shifts up or is spread out this way. Other than that, the shape's the same. Note that on these slides, what's plotted here, there's no absolute value of f. It uses the variable f. Here, I've used f equal to 100. But here, there is no value of f. It's generic. And that's why we see, instead of an absolute value of time, it's 1 times t, where t is the period. But the shape of the signals is the same. We can view the communication signals. This is in the time domain. We can also view them in the frequency domain, where if we have such a signal which is made up of different sinusoid components, then using this structure of adding different components, we say that there are 2 components, one with frequency 100 Hertz, one with frequency 300 Hertz, and we know their peak amplitudes. We can use that to visualize that signal in the frequency domain. In other words, we can create a plot or a graph. Good morning, sit down. Another way to view this signal is in the frequency domain. This is in the time domain, where we have the signal amplitude or intensity versus time. We know that our signal has 2 components. In the frequency domain, we will plot the peak amplitude versus frequency. Let's create the plot first and then explain how it's useful. Well, our signal has 2 components. First component has a frequency of 100 Hertz. So we're going to have something at 100 Hertz. And the second component has a frequency of 300 Hertz. What we do for each component is plot an impulse with a height equal to the peak amplitude of that component. This component has a peak amplitude of 1, the second a peak amplitude of 1/3. So we have an impulse here of height 1, and at frequency 300 we have an impulse of height 0.33. 1/3 of this one. This is a plot of our same signal but viewed in the frequency domain. This equation, this plot, if we substitute in f equal to 100, and this plot represent the same signal. One in a mathematical form, one plotted in the time domain, one plotted in the frequency domain. It is useful for engineers who are designing signals and analysing signals to think about the signals in the frequency domain. It can become easier to compare them and to analyse them and to determine characteristics like bandwidth, which we'll describe shortly. So firstly, this is how to create a plot in the frequency domain. Take the components, identify their frequencies, identify their peak amplitudes, and plot an impulse at that point. And we have a point there. So here's the plot that we just arrived at, but for the more generic signal, where f is a variable. In practice, communication signals are not as simple as summation of two sinusoids. They can be much more complex, and in fact we can have digital signals. So the signals in the frequency domain can be more complex than simply two or a number of impulses. Here's another example of a signal in the frequency domain. And this has an infinite number of components. Our signal here had two components. This is a plot of a signal which has an infinite number of components. We have points all the way and it will keep going out here. This signal has two frequency components. It's possible to have an infinite number of components in theory. Just a different view or a different signal. Let's introduce some new concepts that we can characterize signals with. The spectrum of a signal is the range of frequencies it contains. So we can say that the spectrum of our example signal here, S1 of t, where we're going to write it, up the top. The spectrum of this signal, which is the summation of these two, it contains two components, one with frequency 100 Hertz and another with a frequency of 300 Hertz. So that's it. That's the spectrum of that signal. It contains components with two different frequencies. The next thing that we're interested in is the absolute bandwidth of a signal. That is the range of frequencies that it occupies, starting from the minimum frequency component up to the maximum. So in this example, the absolute bandwidth of S1 is what? 200 Hertz. It's the difference between the maximum frequency and the minimum frequency in the spectrum. In this case, there's only two components, 300 and 100. The difference is 200. So we say that this is the absolute bandwidth of our signal. Our signal occupies the spectrum covering 200 Hertz, a width of 200 Hertz. From 100 up to 300. The signal has a frequency of 100 Hertz, an absolute bandwidth of 200 Hertz. In practice, the spectrum that we can use to send communication signals is limited. because different frequencies are suitable for different applications. Some frequencies travel through walls, some don't. So depending on our application, we only have a certain number of frequencies that we can use for our communication signal. So we normally want to minimize the number of frequencies we use for a signal. Or in other words, minimize the bandwidth used. The more bandwidth we use, the higher the cost normally of equipment that will produce that communication signal. We'll talk more about that when we summarize on this topic. But normally we want to minimize the bandwidth. So just defining two terms, the spectrum, the range of frequencies in the signal. The absolute bandwidth is the difference between the minimum frequency component and the maximum. The width of the spectrum, really. Going back, here's a plot of a signal in the frequency domain. What is its bandwidth, or absolute bandwidth? Well, it ranges from 0, and in fact, here it goes up to 5 over x. In fact, it keeps going. The plot finishes here, but this signal, you can imagine, it keeps getting smaller, but it never reaches 0. It keeps going. So in fact, it has an infinite absolute bandwidth in theory. So to transmit this signal, you need an infinite range of frequencies. But in practice, transmission equipment, the things that create the signals, limit the range of frequencies that are transmitted. So in theory, it has an absolute bandwidth of infinity, but in practice, the effective bandwidth would be limited. For example, what we could do is say, okay, most of the energy of this signal, the peak amplitude is shown on this axis. So the amplitude is highest around this area. Most of the energy of this signal is within this range of the frequencies. Out here, the energy of that signal is very weak. The peak amplitude is very, very small. It's getting close to 0. So we may only transmit this range of frequencies, and that would define an effective bandwidth of that signal. So in theory, a signal has an absolute bandwidth. In practice, many signals have their bandwidth limited by the transmission equipment because we cannot transmit an infinite number of frequencies, and we get what's called the effective bandwidth, or what's just known as the bandwidth. The bandwidth of a signal, when you read about products and communication signals, is what's transmitted in practice. So sometimes it may be confusing that we refer to bandwidth and absolute bandwidth. Absolute bandwidth in theory is just the difference between the minimum frequency component and the maximum. But in practice we cannot transmit all theoretical frequencies depending on the equipment. We're going to show that the bandwidth of a signal limits the data rate. What's data rate? Data rate is the number of bits per second that we can send. We're sending a signal which represents data. The bandwidth of that signal and other factors impact or influence how many bits per second we can send. As computer scientists, you're normally interested in this. You buy a communications link, you care about how many bits per second you can send. Well, where does that number come from? It's related to what is the bandwidth of that signal. So let's go through several examples that try to relate bandwidth and data rate. That's just another example of a signal. I think I showed this yesterday towards the end. This is showing the top signal has two frequency components, sine 2 pi ft plus 1/3 sine 2 pi 3 ft. The second signal here has a third component. You can see some pattern. One 1 sine 2 pi 1 ft, 1/3 sine 2 pi 3 ft, 1/5 sine 2 pi 5 ft. Introducing this extra component, and this is the shape that we get in the time domain. We can see that, okay, well, we cannot see much yet. Let's add another component, the top one. We add a fourth component, 1/7 sine 2 pi 7 ft. And we can see that the shape is getting a little bit more square at the top. Going back. With a single component, it's a single sinusoid. With just one component, it's just the sine wave. With two components, we get some different shape at the top. The three components, it becomes a little bit more straighter here. Four components, more so. An infinite number of components, it becomes a perfect square wave. So, what if we want to use such a signal, any of these four signals? This is, in theory, if we had an infinite number of frequency components, that is, an infinite absolute bandwidth, if we want to use one of these signals to transmit bits. Well, a simple scheme that we could use would be to say, if I want to transmit bit 1, we could use a high value of our signal. If I want to transmit a bit 0, we can use a low value. And we can modify our signal. If I have a bit 1 to transmit, then transmit at the high level. If I've got a bit 0, transmit at the low level. When the receiver receives the signal, they check, is the signal high for this duration? If so, I'll interpret that as bit 1. If it's low, in this case, if it's -1 for this duration, I'll interpret as bit 0. So that's a simple way that we can map our digital data, our bits, to our communication signal. Same with these signals. We could use this to represent a bit 1 and this to represent bit 0. If we want to transmit a sequence like this, we just need to transmit, I'll try and plot it here. It's not exact. Something like that, where we just alternate or we change the sign of our signal depending on the bit 1 or bit 0. 3 bit 1s we'd need to transmit for some duration high, 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 and so on. The receiver receives this signal, measures the signal strength for this duration, measures it to be high, and therefore believes that it's received bit 1. Measures it then to be low, okay, it thinks it's received bit 0. So, one thing that we could say is that within this, well, within one period of our signal, we could transmit 2 bits. One bit, the second bit. If we use this approach, within one period, we could transmit 2 bits. So we want to work out what data rate we can transmit at using one of these signals. How many bits per second can we send? Well, in any of these signals, if we have one waveform, then in one period we could transmit 2 bits at a time. 1 bit and the second bit. Let's put some numbers to these and go through some example. We'll use these slides, but I think on 2 slides forward there's an example that we'll go through. We'll go through 3 different cases. As the designer of a communication signal, the person who designs it and the equipment that's going to transmit it, let's say they get to choose the frequency that they can transmit at, and they can choose which of these signals that they use. Do they use a signal with just 2 components, or 3 components, or 4 components, or whichever? Let's start simple, and let's say that we want to design a signal which has 2 components, as the top one up there, and the one that we just had written here, S1. And let's say we're going to use a frequency of our signal of 1 megahertz. A frequency of 1 megahertz. So if we have 2 components, then it's sine 2 pi times by the frequency, 2 pi ft. 2 times pi times by our frequency, 1 million, 1 by 10 to the 6, times t, and we've got 0 phase. Plus the second component, which is 1/3 the amplitude, sine 2 times pi 3f, 3 times the frequency. 3 times 1 million. 1 megahertz is 1 by 10 to the 6 t. Signal 1, if we use frequency of 1 megahertz, simplify, is sine sine 2 pi 10 to the power of 6 t. The 10 to the power of 6 is just a mega, 1 million. 1/3 sine 6 pi 10 to the power of 6 t. All we've done is taken this equation. I've omitted the 4 over pi, just to keep things simple and I don't have to keep writing it. I've omitted the multiplier out the front and just substituted 1 megahertz where we have f. That's our signal, which has a frequency of 1 megahertz. Spectrum. What's our spectrum of our signal? What's the spectrum of our signal? The spectrum is the set of frequencies contained. What is the spectrum of our signal? The spectrum is the set of frequencies contained in that signal. 1 megahertz and 3 megahertz. Our signal has 2 components. The first component has a frequency of 1 megahertz. The second component has a frequency of 3 megahertz. We say the spectrum is just a list of those frequencies. Let's plot that signal in the frequency domain. If we want to plot it, we know that there are 2 components. The first one has a frequency of 1 by 10 to the power of 6 hertz, 1 million hertz. It has a peak amplitude of 1. The second component has a frequency of 3 million, 3 by 10 to the 6. and a peak amplitude of 1/3. That's the plot of our signal in the frequency domain. What's the absolute bandwidth? If we look at this, visually we can easily see it. We just take the rightmost point and the leftmost, the maximum and the minimum, and find the difference. The bandwidth is the width between, the width of the spectrum. 3 minus 1 is 2 megahertz. So this signal occupies 2 megahertz of our spectrum, has a frequency of 1 megahertz. What's the data rate? Well, we know with our signal, if we represent in one wave or in one cycle, we could represent 2 bits. 1 bit and 1 bit. How do you calculate 1 megabit?
One cycle have 2 bits, 2 megabits per second.
Yeah, one cycle can have 2 bits. Our frequency is 1 million hertz, 1 million cycles per second. That's what hertz is. So we can have 1 million of these every second. Therefore, each one of these contains 2 bits. Therefore, we could transmit 2 million bits per second. Or alternatively, you can calculate, well, what is the period? We said in one period we could transmit 2 bits. Well, we know the frequency is 1 megahertz. The period is the inverse. 1 divided by 1 million, which is 1 microsecond. 1 divided by 10 to the power of 6 is 10 to the power of minus 6. 1 microsecond is the period. We can transmit 2 bits in 1 microsecond. Then how many bits in 1 second? Well, there are 1 million microseconds in 1 second. Therefore, 2 million bits in 1 second. 2 million bits per second is the data rate that we could achieve in this case. If you don't believe me, you could draw the signal in the time domain. Draw this to scale. You'd have, over a period of 1 second, you'd have 1 million of these cycles, and you just count them. Okay, this portion represents 1 bit, this represents another bit, and you'd count 2 million different portions, or 2 million different bits there. So, that's our first case. If I design or choose a signal which has 2 components and has a frequency of 1 megahertz, then that signal will occupy a bandwidth of 2 megahertz and produce a data rate of 2 megabits per second. Generally, we want to maximize our data rate while minimizing the bandwidth utilized. I'd like to be able to send it 100 megabits per second. Well, we'd need to use a different signal or a different frequency and bandwidth to achieve that. Let's see what we can do if we change some things. Where are we going to do it? Here. First thing we can change, let's change the frequency that we use. Same signal with 2 components, except let's set f equal to be 2 megahertz. Then let's get a second signal, S2. We'd have 2 components. It'd be sine 2 pi times 2 million. 2 times pi times 2 by 10 to the 6 would be 4 pi by 10 to the power of 6 t plus 1/3 sine 2 times pi times 3 times the frequency. 2 times pi times 3 times 2 is 12. It's again this top signal where I substituted f equal to 2 million. In this case, I had f equal to 1 million. That's our signal. We plot that just quickly. 2 components. First component has a frequency of 2 megahertz. Second component has a frequency of 6 megahertz. 3 times 2. Scale's not so good. Spectrum is simply 2 megahertz and 6 megahertz. More importantly, the absolute bandwidth is 4 megahertz. The difference between 6 and 2, because we'll run out of space, the absolute bandwidth of this signal is 4 megahertz. 6 minus 2. What's our data rate that we can achieve? Let's calculate it. You're correct, or except for your units. With a frequency of 2 megahertz, 2 million per second, the period is 1 divided by 2 to the power of 6. 1 divided by 2 million. 0.5 by 10 to the power of minus 6 is half a microsecond. One period, one duration here up the top, is half a microsecond. All I did is took the frequency and took the inverse of that. 1 divided by 2 million, and you get 0.5 microseconds. And we know within one period we can transmit 2 bits. So 2 bits in half a microsecond, which means 4 bits in 1 microsecond. And there are 1 million microseconds in a second. 4 bits in 1 microsecond means 4 million bits in 1 second. The data rate of this signal is 4 megabits per second. Absolute bandwidth 4 megahertz. Our first signal had an absolute bandwidth of 2 megahertz and a data rate of 2 megabits per second. Both signals have 2 frequency components, but we've changed the frequency. We went from 1 megahertz up to 2 megahertz. As a result of doing that, we've doubled the bandwidth utilised and we've doubled the data rate. Remember, we want a high data rate, but we want low bandwidth. So we have a trade-off here. Even though we've increased the data rate, that's good, from 2 up to 4, we've also increased the bandwidth utilised from 2 up to 4 megahertz. That's not so good. So we don't get anything for free. We cannot simply increase the frequency to get a higher data rate, because if we do that, we also increase the bandwidth used. So this is showing the relationship between the physical characteristics of the signal, the frequency of that signal, the bandwidth of that signal, and the data rate that we can achieve. a designer of communication signals would need to choose these parameters to achieve the data rate that they require with minimum bandwidth utilised. In those two cases, we use the same basic signal. It would look like this. If we plotted both of them in the time domain, although they'd be on a different scale, they'd both look like this. Same shape, just that the time frame would be different, because it has two components. What if we choose a third signal which has three components? It would look like this. If we have a third signal now, S3, and let's go back to the first one and keep the frequency at 1 megahertz. So I'm going to compare this third signal to our first one. That is, I'm going to use the same frequency, but instead of having two components, I'll have three components. The structure will be the same. Sine 2 pi by 10 to the 6 t plus 1/3 sine 6 pi 10 to the 6 t plus another component. Sine 2 pi 10 to the power 6 t plus 1/3 sine 6 pi 10 to the power 6 t plus, so that is simply these two components. And let's add an extra component following this format, plus 1/5 sine 2 pi 5f t. F is 1 megahertz. 2 times 5 times 1 megahertz, 10 pi 10 to the 6 t. Just make sure you can read what I've done there and understand how I come up with that. Two different signals, S3 and S1. They have the same frequency, these signals, but they have different number of components, sinusoid components. This one has 2, the second one has 3. And the second one, in fact, has these two plus the third, which is following the structure of 1/5 sine 2 pi times 5 ft. F is 1 million. We don't have much room, but we could plot that if we wanted to. 3 components. First one at a frequency of 1 megahertz. Second one at a frequency of 3 megahertz. Third one at a frequency of 5 megahertz. 2 times pi times f. Times 5f, sorry. Here, 5f. The scale here is megahertz. The peak amplitude of the first component is 1. The second component, 0.33. And 1 divided by 5.2 here. 1.33 or 1/3, 0.2, 1 divided by 5. That's easy to plot. If you wanted to plot this, it would not be so easy. You'd need your calculator and you'd need to take, okay, what if t equals 0.1? You'd plot this point and then this point and this point, and you'd go through, eventually you'd join those points so you get this plot, or your computer would do it for you. This one you can do in a quiz if I give you this equation. Or, given this, you could write down this equation. So make sure you understand the relationship between the signal equation and the plot in the frequency domain. I would not ask you to plot this in the quiz or exam. That requires a calculator or a computer.
We need one cut.
Yeah. And from this, we can see that the spectrum is 1, 3 and 5 megahertz, and the width of that spectrum is, what's the width of the spectrum? The bandwidth is 4 megahertz. The bandwidth, maximum 5, minimum 1, the absolute bandwidth of our signal is 4 megahertz. So signal 3 with 3 components using a frequency of 1 megahertz has an absolute bandwidth of 4 megahertz. Data rate?
2 megabit per second.
With the same frequency as over here, 1 megahertz, we'll get the same period, 1 divided by the frequency. We can send 2 bits per period, therefore we're going to get the same data rate as this signal. Frequency is 1 megahertz, we got a data rate of 2 megabits per second. Frequency of 1 megahertz, data rate of 2 megabits per second. Now compare them. Which one's better, signal 1 or signal 3? Signal 1 has... Someone want to correct him? Same data rate, 2 megabits per second, 2 megabits per second. Do we want more bandwidth or less? We want to minimize the amount of bandwidth we use for our signal. The bandwidth is the set of frequencies that we need to transmit the signal. The problem with this is that many people want to transmit signals, and there's only certain frequencies available to you.
Don't need too much bandwidth.
So you want to, if you occupy this bandwidth, that will allow someone else to occupy a different bandwidth. If you occupy much more bandwidth, it reduces what other people can use. As a result, to use the particular frequencies, you normally need a license, and that costs money. So we want to minimize the amount of bandwidth we use. So we could say signal 1 offers the same data rate, but uses less bandwidth than signal 3. That's a good thing for signal 1. Why would we use signal 3? What's good about signal 3 then?
What's good? Less error.
Less error. Why?
Because we have fluctuation, something like noise, less noise.
You're right, but signal 3, and let's try and visualize it, signal 3 is a more accurate representation of what we're trying to transmit. What we're trying to transmit is, for some duration, a high level to represent bit 1 and a low level to represent bit 0. That's signal 1, this is signal 3. This signal is closer to our perfect square wave, where it's always high and then always low. So this is a more accurate representation of the perfect case of high, low. We can say this is an approximation of the square wave on the next slide. This is closer to the square wave than that one. Therefore, even if we have errors, we transmit this, there are some errors across the link, and what's received goes up and down, then it's more chance that even if there are errors or noise in the system, then what we receive we'll be able to interpret correctly to being bit 1, bit 0. If we have a signal which is less accurate or a less accurate representation of our perfect square wave, then it's more chance that if there are changes in that signal due to noise, then the receiver will interpret some part of the signal to be bit 0 when it's in fact means bit 1. So what we'd like is a signal which looks like this, because for this duration the signal is always high at +1. To get this, what we've done is approximate it by using a signal which doesn't have an infinite number of sine components. This one needs an infinite number of sine components. That's not possible. We've approximated in the first case using 2 sine components, and in the second case using 3 sine components. In the first case we get the top one. In the second case we get a signal which is a little bit closer to our ideal case, and therefore less chance of errors occurring if we have noise introduced in the system. We'll see another example of that shortly. It's hard to visualize. But in summary, signal 1 provides the same data rate but with a lower bandwidth. That's good. But signal 3 is more accurate than signal 1. Less chance of errors occurring with signal 3. We don't have a way to measure that. That's a characteristic of this signal. So we have this trade-off here. Want to maximize the data rate, minimize the bandwidth, and maximize the accuracy, which minimizes errors. How do we do that? To increase the accuracy of our signal, include more sine components. Going from 2 to 3 gives us more accuracy. Increasing the frequency, we saw, increasing a frequency from 1 up to 2 increased our data rate, but it also increased our bandwidth. So we have these different factors coming into play, and there's no single solution of which signal is best. Therefore, the designers need to choose an appropriate trade-off. We'll summarise that in a moment. Any questions on how those calculations were performed? In your next quiz, for example, here's a signal, write the equation for that signal. Or the other way around. Here's a signal, draw the frequency plot, the plot of that signal in the frequency domain. Here's a signal and some frequency, what's the data rate that we can achieve? Or, here's the signal, here's the bandwidth that we have available, what frequency to use, or what data rate can be achieved. So we can relate these 3 factors, absolute bandwidth, data rate, frequency, and the signal together. This was the example that we went through, except up here you've got different numbers. That doesn't matter. I said with a bandwidth of 4 megahertz and a bandwidth up to 8 megahertz. In fact, what we've done is we looked at the frequency, set the frequency. We had a bandwidth of 2 megahertz, changed the frequency and got a bandwidth of 4 megahertz. So I've just used different numbers than what this slide says. We'll come back to this one in a moment. So to summarise the trade-offs, when people design and choose communication signals for different technologies, they need to consider the bandwidth. And in practice, transmission systems impose some limits on the bandwidth. We cannot transmit at an infinite bandwidth. The bandwidth is a limited resource. We cannot use any frequency we choose. Normally, if you buy a laptop and it has wireless LAN, then the standard and laws specify you can only transmit in a certain range of frequencies with a certain bandwidth. It's around 2.4 gigahertz is the frequency of wireless LAN, and the bandwidth of each signal is, I think, around 20 megahertz. You cannot use more than 20 megahertz for the bandwidth. If you did, you get a higher data rate, but you'd be breaking the law. So technologies are built because wireless LAN is only allocated a certain bandwidth to transmit on, because at a different portion of the spectrum, there's other technologies transmitting. Mobile phones, satellites, TV stations, and so on. So all the technologies are allocated some portion of the spectrum. Therefore, there are limits on the bandwidth for each technology. As there are limits, it's a limited resource. There's some cost. The more bandwidth you use, the higher cost incurred. So we'd like to minimize the bandwidth, because the greater the bandwidth used, the greater the cost generally. The data rate is related to the bandwidth we use. The greater the bandwidth, the greater the data rate in general. So there's the trade-off. We want to minimize cost but increase the data rate. And another thing which it's harder to, we didn't calculate, but we said that we also care about accuracy.
Why greater value and greater data rate?
We saw here, which one did we see? In comparing signal 1 to signal 2. We increased the frequency, and that allowed us to have, or that meant that we occupied a larger bandwidth, from 2 megahertz up to 4 megahertz. It allowed us to increase our data rate from 2 megabits per second up to 4 megabits per second.
Okay, the same equation.
Yeah, yeah. In that, comparing the same equation in that case. So in general, if you've got more bandwidth, you can send faster. But it's going to cost more to use that bandwidth. And we'd like to have signals which are accurate. That is, if there are transmission impairments, that is, we transmit a signal, but between the transmitter and receiver there's some noise. And that causes the received signal to be different from what was transmitted. We'd like the receiver to be able to correctly interpret the bits that were sent. So some signals are more accurate than others, and therefore less chance of errors.
Why we don't send by the DC? This is for AC.
If we go back a couple of slides, we'll see that some signals, if they can have a DC component. I think in some circuitry that causes problems at the receiver. So it's harder to deal with that component. So we avoid that. It's easier to deal with the signals without the DC component. Yeah. Go back to one slide we skipped over. This shows maybe a little bit better this idea of accuracy and the relationship between bandwidth and accuracy. Here's some sequence of bits that we want to transmit using some signal. So we can represent that as this pure digital waveform of, in fact, it's opposite of what we used. Bit 1, low, bit 0, high. So it's just some random sequence of bits. This is what the pulses would be that we'd like to transmit. This shows the signals that would be transmitted if we have some limited bandwidth. If we had infinite bandwidth, we could form this perfect digital waveform. With an infinite bandwidth, we saw we can produce a perfect square wave. But we don't have an infinite bandwidth. If we had, in this example, if we had 500 hertz available to our system, this is what the transmitted signal would look like. And this is an approximation of this data. If we increase the bandwidth we get our approximations to be closer to what we want. You can see this one is a little bit closer. It's a peak here when we have our bit 0 and another peak here. Whereas this one, okay, the peak is here and here, but there's not much difference from this point and this point. Increasing the bandwidth allows us to transmit a real signal which is a closer approximation to the representation of the digital data, what we want to transmit.
So this frequency is 1 kilohertz.
We haven't defined what the signal is in this case. So we're not looking at what is the value of the frequency or how many components are there.
Enough from bit delay 2000 to be.
Yeah, so what have we got? 2000 bits per second. What we're going to see later in one other topic is that what we did is we had one level and we encoded 1 bit. Later we'll see that in one level we could encode more than 1 bit. So it's not as simple as one level, 1 bit. So I don't want to make assumptions there. Ignore that for now, but let's not worry about frequency here and simply relate data rate and bandwidth and accuracy. We can see that with a higher bandwidth, we've got a signal transmitted which is more like the desired signal. It's more accurate. If there's some errors, that is, we transmit this signal, but what is received, if we can draw it, errors or noise in a system cause some random variations of what's received. So if we transmit, say, this signal, then maybe what's received is, let's draw what was transmitted. That's my picture of what was transmitted. And now, what if, we've only got 5 more minutes and we'll finish. If we add some random variations because we transmit this and there's some noise in the system, so what's received, maybe it goes up and down. So I've added some random variations. Then the receiver receives the red signal. And what it does, it looks over this period, is the signal low? If so, I'll interpret that, in this case, as a bit 1. If it's high, bit 0. In this case, we may be okay, that, okay, this looks to be, if we split here, okay, most of the signal is low here, most of it's high. No errors here. I think I've got the right number of, sorry, I've gone backwards. And we see we represent bit 1 by a low signal in this case. How many bit 1s? 4. If we used a lower bandwidth, 500 Hertz, then what have we got? We've got something. That's our transmitted signal, the one at the top. Add some random variations to that. Now the receiver receives the red signal. It's much harder to determine, is this all high or all low? Does this represent a bit 0 or a bit 1? So there's a chance or a greater chance that the receiver will make a mistake and think, okay, this is, all right, this is, most of it's high, therefore bit 0. Most of this is high, 0. All right, this is low, 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 low. and what's interpreted by the receiver is different from what was transmitted. Because the signal that was transmitted was not very accurate. It did not accurately represent our pulses. This one with a larger bandwidth was more accurate. Increasing the bandwidth can give us more accuracy in the signal, so we can design different signals, but of course we want to minimize the bandwidth because that increases cost. So that's where we're going to finish today, because the IT section are at the same level. I keep everyone together. Next week we'll finish on this topic of data transmission, looking at the final parts of different analog and digital signals. Come and see me if you have any questions about that. We still have some time to discuss.